Another useful trick comes in when we combine implicit differentiation with taking logarithms. Let's do an exercise first, which shows us the main results. Suppose that y is the natural logarithm of f of x. Use the chain rule to show that dy by dx is f dash of x divided by f of x. In particular, if y is a function of x, then the derivative of the logarithm of y with respect to x is y dash over y, or if you like, 1 over y times dy by dx. Sometimes we can take logarithms and use our laws of logarithms to simplify expressions. So let's take logs here. So if we take logarithms, we find that the natural logarithm of y is the natural logarithm of x plus the natural logarithm of x plus 1 minus the natural logarithm of x squared plus 1. Now we can differentiate log y. We've just explained how to do that. We get 1 over y dy by dx. So differentiate. We get 1 over y times dy by dx. Now remember, when we differentiate log, this is one of our standard differentials, log x becomes 1 over x. We can differentiate these with the chain rule. So if x goes to x plus 1, and then log of x plus 1, so that's like combining two functions. When we plug that into the chain rule, in fact, this just turns out to be 1 over x plus 1. This one as well, this is x goes to x squared plus 1, and then log of x squared plus 1. And we can do that in the same way. And what we find, in fact, is that it's minus 2x over x squared plus 1. Well, now we can easily work out what the dy by dx is. We just simply multiply all the right-hand side by y. So multiplying by y, and then you put everything over a common denominator, which I guess is going to be x squared plus 1 squared, and then you can read off what dy by dx is. Sometimes logarithms are useful to simplify really complicated expressions that you just wouldn't be able to do otherwise. So one example, suppose that y is x to the power x. So that's a really funny function, probably not a function that you'll ever meet in engineering, but it's the kind of function that lends itself rather well to taking logarithms. Because log of y is x times log x, if you remember your power laws. And then we can differentiate this. So differentiate. So log y differentiates to 1 over y dy by dx. And on the right-hand side, we have a product of x and log x. And we know how to differentiate a product. It's f1 times f2 dash. So f2 dash is 1 over x, if f2 is log x, plus f1 dash times f2. So this is just x times 1 over x is 1. This is just 1 plus log x. And so we can read off then, just multiplying up by y. So dy by dx is y times 1 plus log x. And writing all this in terms of x, we get, so y is x to the x. So this is x to the x, 1 plus log x. So again, by taking logarithms, differentiate sine x to the power x using the same method. Taking logarithms gives another way of proving the product law. So suppose that g is f1 times f2. Well, then log of g is the log of f1 plus the log of f2. Well, as the derivative of log g is g dash over g, and the derivative of log of f1 is f1 dash over f1, and the derivative of log of f2 is f2 dash over f2, you should be able to differentiate this and rearrange the answer and show that g dash is indeed f1 dash f2 plus f1 f2 dash. And you might like to extend this to work out the derivative of a product of n functions. So f1 times f2 all the way up to some fn all dash.